Where should I begin? How should I know that sin lies within? So tell me, where should I start? What should I do first? How should I know that we were close? Where should I start? Where should I begin?
Okay, you'll have to let me know if anything, if you can't hear anything. I tried my best to get the sound working earlier, and it seemed like it worked. So I don't know. I'll have to. This is going to be, a learning process. Unfortunately, I mean, normally this would be pretty easy to set up on pretty much any computer, but I my my computing needs are very niche, so I have kind of everything set up in a way that it is very, very specifically set up for the things that I do. So having it work uh, specifically when it comes to this stuff, which requires Windows to be updated and my video card drivers to be maximally updated and stuff. And the stuff that I do on this particular computer, um, it doesn't like legit stuff. So it hasn't, prior to these last couple days, it hadn't been like legitimately updated in 2.5 years. So that was tricky, and unfortunately, I'm pretty sure that I've ruined like all of my installs with this. But this is the sacrifice I'm making, for your class. But I'm good. I'm glad that it works. Okay. So first, I guess before I actually start, since I have like 3 more minutes, I guess. Basically, what I'll say is I'm testing this out. This is probably how I'm going to proceed for the remainder of the semester. Sometimes, if I feel like I didn't cover enough, what I'll do is uh, basically I will I'll basically just record a bunch of lectures separately and upload them. Um, at some other time, so I won't live stream those. I'll just record them and upload them and let you know. But I'm not gonna, none of the burden of this stuff is gonna fall on you. So any recording of lectures that I do, I'm not gonna like pile like a ton of lectures on you at once and say, okay, now homework is due next week on like a pile of 10 lectures or something. So not gonna work out like that. So it will be done in a nice way. You're not gonna have any homework that I'm gonna have due until maybe after next week. Um, anyway, so let's see what else. For this class, I don't think it makes a whole lot of sense. For maybe my large lecture, I may end up doing some kind of flipped classroom where I record most of the lectures and then hold problem sessions instead. Doesn't really make sense to use. Why not use Zoom? So the thing is that I'm already having to do this for a large lecture class of mine that's like 300 students. Um, so basically, I was gonna have all of my students be on one platform since I'm gonna basically try to do this for all of my classes. And the problem is Zoom, I think, can only accommodate up to either 50 or 100. I can't remember the limit, but I know that there's a limit, and it's certainly less than 300, which is, I think I have 289 students in my 246 class. So yeah, since I was going to be using YouTube anyway for my 246 class, I decided to just go ahead and use it in this way, since it's going to have the same, now that I've got it working, it's going to have the same functionality. And this document camera I'm using was actually shipped to us by the university, so I just got it a couple days ago and got everything set up. Let's see, what else was I going to say? Yeah, so the hosting like problem sessions or whatever doesn't quite make sense for this course. Um, So no, I mean, if it turns out that this doesn't work out that great, I can always I can always switch to Zoom. I know that I'm having my TAs use Zoom for discussion in 246. So if for whatever reason this doesn't quite work out, then we could always switch. So yeah, that's one thing. As I mentioned in my post earlier, is I would, I'm going to expect both on both ends. So I will be flexible with my expectations, and if you're flexible with your expectations of what I can accomplish in this way, then I would be very, very grateful for that. Yeah, the exam one grades, they are stuck in my office. I hope to go sneak onto campus soon and grab them. So that's the deal with your exam ones. So yeah, I will. They're graded already. They're just literally sitting, waiting for me to pick them up. This was like the last thing that happened essentially after I'd already left campus. The grader put them in my mailbox, and that is where they sit. So anyway, um, what what else did I want to say? Um, so then the only remaining things that you're going to be graded on for the rest of the semester, there will be the homeworks, which, like I said, I won't have you guys turn in. You won't be turning in anything for at least like a week and a half, 2 weeks. And the you were gonna have two more midterms and a final, so that's just gonna be one midterm and a final. That midterm won't be till maybe after the third week of April. What else? That's the important stuff for now. The final and the midterm are going to basically have the same type of format. I'm going to post a document to Elms, and you will have like a couple of days, like 2 or 3 days, to do it, and then upload your solutions. Yeah, so that's the main bit. So anyway, yeah, I have a VR headset, and I thought I saw someone lecturing in the VR game Half-Life Alyx, and it looked like it could work possibly, but yeah, I didn't want to attempt it unless this totally fell through, but that was technically an option, I guess. Okay. So, 4.2, which is more or less where we stopped that last Tuesday, where we were actually doing stuff. So 4.2, I'd already done a little bit of motivation for basically. So 4.1 was all of the basic derivative rules. So all of the stuff for so it's product rule, quotient rule, derivatives splitting across sums, factoring constants out of derivatives, those sorts of things. So the next thing that I wanted to talk about was derivative of inverse functions. So we had already done a couple of examples, so maybe I'll remind you of those. So if I have function f of x is 2x plus 1, something simple. All right, so what does this look like? Well, we know what this line looks like. So it's just a line of slope 2. So the derivative of this thing is constant, as we know from the first section. So then we can actually just compute what its inverse is explicitly. So its inverse is explicitly this. Oh, let me adjust this. I see I'm pushing it a little bit off screen. So anyway, if I have an explicit formula for the inverse of a function, then assuming that I actually know how to compute the derivative of that function, then I have no problem at all. So here, this is just another linear function, so I have no issue computing the derivative. And I see, oh, the derivative of this thing is also constant, and it's just the reciprocal, right? So the derivative of f of x is 2. Derivative of f inverse is 1/2. So if I consider function x squared for positive real numbers, um, of course, you already know why I'm restricting myself. All right, so this is a strictly increasing function, so this is strictly monotone. Okay, we know why that's important. So note from section 1, I already know what the value of the derivative of this function is at, say, 3. Okay, so derivative of, or the value of the derivative of this function at 3 is 6, because the derivative of this thing is 2x. So, okay, if I know that the value of my derivative here is 6, how can I compute the value of the derivative of this inverse? You already know how to, should say that you can cheat a little bit because you already know what the inverse function for this thing is. But unfortunately, we technically don't really know how to compute the derivative of that thing. So you already know, right, that the inverse function is positive root y, right? You already know that that is the inverse of this thing. But we don't really know how to compute the derivative of this yet, so that's actually coming later. And so what I want to say about this derivative, I can't really say directly, right? So the idea is I expect the derivative of f inverse y at the point 3. Well, I want to know what point this lies on the graph of my function x. So here at 3, this function is 9, so it's the point 39 that I'm looking at. So at that point in the plane, I want to know what the value of the derivative of this thing is. So that is f inverse prime of 9. I expect this thing to be what? If the value of f prime is at 3 is 6, then at the same point corresponding to the x value of 3, I expect this thing, just based on my previous example and based on the picture I drew, this is like one of the last things I drew in class, I expect this derivative to be 1/6. Okay, this reciprocal. Okay, so then how do I actually show that? This is some algebraic trickery. If you're looking in the textbook, you'll see exactly where I'm going with this. So basically, note that note if y is positive and y is not equal to 9, then y minus 9 can be rewritten using some algebraic trickery as root 9 plus 3, root 9 minus 3. So this is difference of squares, right? And what that means is that if I'm looking at f inverse y minus f inverse of 9 over y minus 9, this is, so I've already said that f inverse y is root y. I have f inverse of 9 is root 9, which is 3, over y minus 9. Again, using this algebraic trickery here, this is root y minus 3 over root y plus 3, root y minus 3, So these cancel. I'm left with 1 over root y plus 3. So if I take the limit as, oh, I'm moving off. I'm not too far down. Okay. So if I take the limit as y approaches 9 here of this quantity, I'm not going to rewrite that. What I get is 1 over root 9 plus 3, so this is 1/6. That's exactly what I expect. Okay. So both of these examples are telling us the same thing, which is that in this simple example, I know what the value of the derivative is. It's just slope of this line, so it's just 2. Here, this is another line, and it turns out that, well, it has slope 1/2, so it's just the reciprocal of the derivative at the corresponding value. So the same thing is going on here, right? So I have the value of the derivative of f is 6, value of the derivative at the point corresponding to f, which, note, and you might remember this when you first saw it, well, in Calc 2 at UMD, this is done in Calc, sorry, so at UMD this is done in Calc 2, but you might have seen it in Calc 1. Basically, note that, this derivative we're computing is the derivative at 9, not at 6, because, that point might not even be on the graph of the inverse. So the point is that this is at the point corresponding to this x value, so this is the value of the derivative of f inverse at 9 instead. So anyway, so that's what you're being told here. So basically, this is illustrating following fact. So here's the theorem in question. So let I be a neighborhood. You might recall the definition of a neighborhood of a point. So let I be a neighborhood of x naught, and let the function f from I to r be strictly monotone and continuous. Okay, so suppose that f is differentiable at x naught, and that its derivative is non-zero. Okay, so define J to be the image of the neighborhood I under F. Then the inverse F inverse, which goes from J to R, is differentiable at the point y naught, which is the image of x naught under F. Okay, and exactly what I expect. The derivative of F inverse at y naught is 1 over the derivative of F at x naught. Oh, I'm totally off the screen. All right. So going through these assumptions here. So I is a neighborhood of x naught, which is an open it's an open interval containing x naught. So F is strictly monotone and continuous. So recall from the previous chapter that one of the last things we talked about was the relationship between strictly monotone functions and functions being one-to-one. And this was the thing that allowed us to define the inverse. And if you had a continuous function that was, say, strictly monotone, this allowed you to define an inverse function that was continuous. And practically speaking, what that meant was if you took a more general continuous function and you could split it up into pieces where it was strictly monotone, you might remember doing that in Calc 1 when you analyzed a function using the, say, the first and second derivative tests. So when you analyze a function like that, one of the things you did was literally split up the function into pieces where it was where its first derivative was positive, negative. So this told you where it was strictly increasing, strictly decreasing. What this is saying, or what this fact showed in chapter 3, was that locally you had an inverse for such functions. So you could, say, consider just the piece of that function where the function was strictly monotone, and that gave you a continuous inverse in a neighborhood of a point where you had it being strictly monotone and continuous. So we already had that we could do this locally for continuous functions. We very much need this to be strictly monotone, or well, I should say that this is one way of guaranteeing it. Really what we need is the function to be one-to-one. That's the thing that does it. If the function's one-to-one, then everything works out nice. And you might remember some of the examples we drew back then of the things that can go wrong. I mean, one very basic thing that can go wrong if you don't have this assumption is that the inverse is not even a function, right? So just think of the very, very basic picture you have here, right? Let me block this off. So, if I just look at something stupid that's not one-to-one, so here's function, it's not one-to-one, then what should the inverse of this function be? Well, of course, graphically it should be this thing, right? Now, this thing is a problem because it's not a function. It's not the graph of a function. So anyway, so that's just one of the things, of course, that could go wrong, which is why if we took, say, this half of the graph, then the nice inverse that we do get is this top portion, right? We could have, of course, done the same thing with the left. Okay, so anyway, so with these two assumptions, what this is saying is that not only do I get an inverse that is continuous on some neighborhood, J, but it's also differentiable. So we already knew this statement if the statement was that the inverse was continuous, but this is saying something more. It's saying it's actually differentiable, and we know what the derivative is at such a point. Okay, so then how do we know this? So proof. So first of all, note that by the intermediate value theorem, what do I know about J? So I already kind of spoiled this earlier when I was saying it, but by intermediate value theorem, if I is a neighborhood of x naught, since f is continuous, then this J, which is its image, is a neighborhood of y naught. So J is a neighborhood of y naught. Would it be possible if the notes could be uploaded to Elms after class? Yeah. So you mean these notes that I'm actually writing on? Yeah, I could do that. I don't have access to a scanner here, but I'm pretty sure I could easily. I'll just take pictures of it or use some app to make it a PDF and upload it. Yeah, I can do that. Okay. All right. So yeah, by intermediate value theorem, J is the neighborhood of y naught. So what does, of course, y naught is the image of x naught. Note, or rather I should say, define for a point y and j with y not equal to y naught x is this image point. Okay, so let x be the image of a point y in the neighborhood j under this function f inverse. We know f inverse is a function because it's strictly monotone and continuous by assumption, right? So we know that this thing is a function. Okay. So now what? Note that f inverse y minus f inverse y naught over y minus y naught, well, I can write this in a very particular way. So noting that this is what I have going on, I can say this is, rather this is x minus x naught, right? I'm going to use the same convention, so f inverse of y naught is x naught here. So this is x minus x naught over y is, so y is this thing here. So what is y? If x is f inverse y, y is f of x minus f of x naught. And so really this is 1 over f of x minus f of x naught over x minus x naught. So here's the, you see already exactly where this is going. Because using this definition here, I've literally, this thing is exactly what we're trying to show. So this is kind of like a shortcut, if you like. Here, this derivative, of course, which I know I obtained by taking some limit of this thing, is, I'm trying to show this is 1 over f prime of x naught, but that's exactly what I get here when taking this limit and using just the basic quotient rule for limits, right? So now all I have to do is use substitution or composition rule for limits, and I'm essentially done. So since we've already used that f inverse is continuous, so since f inverse is continuous, the limit as y approaches y naught of x is equal to the limit as y approaches y naught of f inverse y. We can move this inside now, so this is just f inverse of y naught, which we have defined to be x naught, right? Okay. So now all that is left is the following. So this is just bookkeeping. So thus by the substitution rule for limits. So remember, the substitution rule for limits was saying that basically if you are taking the limit of some quantity as it approaches some value, but the quantity depends on some other quantity, then you can compare what those two quantities are approaching, and you can replace one of those quantities with the other, right? So this is like if you know that x is approaching 0, taking the limit as 2x is approaching something, right? What does 2x go to? So as long as you were careful with what the expression was approaching, then you could do this replacement or this substitution. Okay, so anyway, so then what is this, what do I get here? So I have the limit as y approaches y naught of f inverse y minus f inverse y naught over y minus y naught. So this is equal to the limit as y approaches y naught of this, recall this expression. So this is 1 over f of x minus f of x naught over x minus x naught. Okay. So here is where my composition rule for limits has to come in. So if I have y approaching y naught, the question is, what does this become over here when I have no y? Right, so having no y here, if y is approaching y naught, then since x is, recall, x is f inverse of y. So if y is approaching y naught, then x is approaching f inverse of y naught, which is x naught. So this becomes the limit as x is approaching x naught of this quantity. So this is the composition or substitution rule for limits. So this is exactly 1 over f prime. Okay. All right. So that's it. That's a proof that this thing is both differentiable, and we actually have a nice expression for computing this derivative. All right. So, quick corollary of this, it's listed immediately after it in the textbook, is a lot of times the inverse function is the thing that you're actually interested in. So in a sense, it's like the primary object. So you can think of a number of examples of this, right? E to the x, for instance, showing up as the inverse of the natural log. So in this case, a lot of times the function in question that you're trying to analyze is the inverse function. And so you will just consider the variable to be x, right? You're not thinking of it in terms of its relationship to its inverse, so or to the original function. And so a lot of times you're just going to see it as the primary object, so there's just going to be an x involved. So that's what this corollary addresses. So let I be an open interval, and suppose that the function f from I to r is strictly monotone and differentiable with non-zero derivative everywhere. Okay. Define J as before to be the image of I under that function f. So then the inverse function f inverse going from J to R is differentiable everywhere. It's differentiable on J. And f inverse prime of x is 1 over f prime f inverse of x for all x and j. How is this different from what I said in the theorem? Well, it's not. It's literally the exact same thing. It's just that instead of having this association where in the previous statement, let me write that. In the previous statement, on the right-hand side, there's an x naught, and on the left-hand side, there's a y naught. This is just me writing this in such a way that I don't have to worry about that. So, and in fact, if I actually replace, if I just do a straight swap of if I have, x playing the role of, or x is f of f inverse of x, and f inverse of x plays the role of x naught, then it's the exact same. It's the exact same statement. So there's not even, I don't even need to prove anything here. So we can immediately use this in a nice way. So immediate application of this is for a natural number n. I can define following function, which is nth roots. Okay. So I can define this for all positive x. Then g of x is differentiable. So this goes from 0 to infinity to r. So positive reals to r. This is differentiable. And its derivative is exactly what you think it is. Okay. So how do I know this formula, right? So technically, remember, you might look at this and say, like, why can't I say that without using either of these things that you just proved? So technically, the derivative rules we know, the thing that you're trying to apply here is the power rule, but remember specifically that the power rule only applies to positive integers, right? So positive integers there, okay, so integers, period, is what the power rule applies to. So here we have something that's not an integer, it's an 1 over n here, and I didn't have any way previously of writing this derivative out. The power rule doesn't apply in this situation. So then how can I use this these two facts that I've just shown here to prove this? So quick proof, actually. So if f of x, which is x to the n, then f is a function from 0 to infinity to r that is very nice. So this expression, or this function rather, is something that the power rule applies to, for instance, and actually you know a lot about this already. Note that g as defined here is the inverse of f, I should say. I'm not going to rewrite that. So note that g of x is the inverse of f, and g also goes from 0 to infinity to r. Thus, g prime of x is equal to, this is by the corollary, so this is 1 over f prime of g of x okay, but then this is 1 over, so f prime, f is x to the n. By the power rule we know what f prime is, so f prime of x is n times x to the n minus 1. So then what do I have here? I have 1 over n times so f prime of x with g of x plugged in is x to the 1 over n to the, so this is to the n minus 1. Okay. So this is 1 over n. This is in the denominator, so what do I get here? I get x to the n minus 1 over n. So that's x to the 1 minus 1 over n. So this is x to the 1 over n minus 1. Right. Which is exactly what I wanted to show. Okay. So I know I wrote this here. Maybe I'll rewrite this bit since I kind of crammed it in there at the bottom. So rewriting this, this is g prime of x is 1 over f prime of g of x, and so this is 1 over n times x to the 1 over n to the n minus 1. So this is 1 over n is x to the n minus 1 over n. So this is 1 over n to the, or times x to the 1 minus 1 over n. But since I'm in the denominator here, this is 1 over n times x to the 1 over n minus 1. Okay. So that's how that works. Okay, and this is nice because otherwise you had no way of figuring this out, right? This is not the power rule. This is something else. Even if it behaves similarly to the power rule, this is something else. You already know that this also works for rational powers, but again, this is a different thing. So I can't just say that this is due to the power rule. Okay. So, what's next? Okay. So, derivatives of compositions of functions. What we just did took care of inverses. The next very important example of algebraic operations you can do concerning two functions is composition of two functions. You already know what I'm going to say here. So this is the chain rule. So chain rule it's probably a better name to call it the composition rule, since it's telling you literally how to compute the derivative of composition of functions. So I'm going to state the chain rule first, and then go about proving it. So you already know how important the chain rule is for subsequent computations. So I had mentioned earlier that now we know how to compute the derivative for nth roots. We are going to be able to do this for rational powers using the chain rule. Really, really simple application of the chain rule. In fact, I believe that's done here in the text. Yep, that's done here in the textbook. It's the exact same thing I was thinking. Okay, so what's the statement of the chain rule? So let I be a neighborhood of x naught, and suppose that the function f from I to r is differentiable at x naught. Let J be an open interval such that the image of the neighborhood I under F is contained in J, and suppose that the function G from J to R is differentiable at the image point f of x naught. Okay. Then the composition G composed with F, which goes from I to R, is also differentiable at x naught. And its derivative at x naught is the derivative of G at f of x naught times the derivative of f at x naught. Okay. So I have no doubt that all of you remember this, because this was something that was used over and over and over again, literally in every computational based math class you've ever had. This is something that's used a ton. So this is definitely something you're familiar with. So I don't have to go over this expression itself, but why does it work out in this way? Okay, so to see that, go about proving this. So let's define y naught to be the image of x naught. And for all x and I, it's different from x naught. If y is similarly defined to be f of x, then since f of x minus f of x naught over y minus y naught is equal to 1, we have, so before I continue on here, I'm going to stop for a second and say, okay, so what am I saying here? So I have an expression, f of x minus f of x naught over y minus y naught, and I'm saying that's equal to 1. Well, y naught is f of x naught, and y is f of x. So yes, this is just a crafty way of writing 1, since this is y minus y naught over y minus y naught. It's clearly 1. But what is it, whenever you have a proof that starts out with some kind of statement like this, what is it that's going to happen? Right, so what that means is that the proof relies at least a little bit on some algebraic trickery. So here's the first bit of trickery. And the reason, or I should say, where might you have come up with this organically without me? So because I'm just going through the proof as it's outlined in the textbook. I have access to this info, so I'm going, from start to finish in this nice, concise way. But if you're trying to prove this on your own, how might you come up with this? The idea is that you have an expression involving these compositions of functions that is something that's not, it doesn't look like there's anything you can do with it, is the problem. So a good example of where you have seen tricks like this before is back when we were proving things about sequences. When you had these combinations of sequences, so there's a way that you could prove the product rule for limits of sequences using a similar trick. The idea was to pull apart the product. You had to add in and subtract off these mixed terms. Okay, and that allowed you to algebraically split it up so that you could use the facts that you wanted to. So a similar thing happens here, except we're not going to add in and subtract in anything. We're going to do the multiplication version of that, which is I'm going to multiply and divide by something, and it turns out that that's just 1. Instead of adding and subtracting, getting 0 right here. Because it's happening multiplicatively, the identity is 1, not 0. So so anyway, this is going to be basically our example of a mixed term here. So you'll see how this works when I write this out. So what does this mean? So we have g composed with f of x minus g composed with f of x naught over x minus x naught. This is the expression that we want to show something about, right? Because this expression, when I slap a limit as x approaches x naught here, this is going to be what I have on the left-hand side here. Okay, so this is the difference quotient that I'm looking at. Okay, so then using this slicker, abbreviated notation, then this is g of y, since y is f of x, so this is g of y minus g of y naught, okay, over x minus x naught. And I noticed that in the textbook there's an obvious mistake, typo. They have x minus x in the denominator, but it clearly has to be x minus x naught here. So this is equal to the same expression, where I have swapped my denominator with y minus y naught. Oh, but how can I do that? Well, I can do that in the following way. So what did I do here? What trickery did I do? I just multiplied by 1, right? So I multiplied this expression by 1, but this particular form of 1, so f of x minus f of x naught over y minus y naught, I multiply by that here, and then I move the denominators around, right? So I took the denominator here, y minus y naught, and moved it over here, and took the x minus x naught that was here and put it over on this numerator, f of x minus f of x naught. So you see exactly how this works. Maybe I should do that in 2 steps, right? So this is g of y minus g of y naught over x minus x naught times f of x minus f of x naught over y minus y naught. And then I swap. Okay, I swap the denominators. So what happens when I do that? The reason for swapping the denominator is obvious. It immediately gives me something. This expression, when I take the limit, is going to become what? It's going to become g prime of y naught. All right, so this is going to become g prime of y naught, and this is going to become f prime of x naught. Okay. All right, that's the idea. Okay. Now, it turns out that I have to do a little bit of bookkeeping here to make sure that all this works out, but basically when you've written out this expression, you're pretty much done with the proof. Okay, so you're basically done. Unfortunately, what has to be done to completely rigorously show this is a little annoying, because it's the bookkeeping to make sure that all of these quantities are not misbehaving. What do I mean by that? Oh. So here's what I mean by that. So note our algebraic expressions are valid so long as Oh, I'm off screen. So note that our algebraic expressions are valid so long as the following holds. So we want y minus y naught to be non-zero. Well, what does this mean? This means f of x minus f of x naught is non-zero. So as long as we have this, we are good. So if there exists, maybe I should say note. Also, if there exists an open interval containing x naught such that f of x minus f of x naught is non-zero if x and x naught differ, then I am done. Via taking limits, right, which is the whole point of writing out that expression. Okay, and all I have to do is use composition product properties. But once you're at that step, you're good to go. Okay, so then what is the only thing left to do? It's to try to come up with what could possibly go wrong. So long as we have an open interval containing x naught on which this is true, I'm done with my previous expression. Let me bring that back for a second. So I'm done in this previous expression because when I write this out, here this thing becomes g prime of y naught. Remember, y naught is f of x naught. So this becomes g prime of f of x naught, and this is times f prime of x naught. So product property of limits and substitution rule for limits, I get exactly what I want here. Okay, so I'm done in that case. So then the only possible barrier to me being done is that no such interval exists. Okay, so then what is our out? Okay, so our hope is to address the possibility that no such interval exists. Okay. So apart from that algebraic trickery, this proof so far has been more or less straightforward. This is a little less straightforward. This is just a kind of an annoying bit of bookkeeping that has to be done. We define h to be a function from j to r such that h of y is g of y minus g of y naught over y minus y naught for y and j with y not equal to y naught, and it is equal to g prime of y naught if y is equal to y naught. Okay, what is it that I'm doing here? So you understand what each of these pieces does. So when y is away from y naught, h of y is this difference quotient involving g. And when y is equal to y naught, it's literally just this derivative. So what is it that h is doing, right? H is just this expression that is encoding my derivative using the definition of derivative, right? The limit as y approaches y naught of this difference quotient. This is what h is. This is what we're putting into h. Okay. So note. G of y minus g of y naught is h of y times y minus y naught. And this is true for all y and j. Okay, well, this is again just some algebraic trickery here, but this is, how does this help me? So note further that this allows me to rewrite the previous expression. So the previous expression can be rewritten in the following way. So I get g composed with f of x minus g composed with f of x naught over x minus x naught can be written instead as h of f of x times f of x minus f of x naught over x minus x naught. Okay. And this is true for all x not equal to x naught and I. Oh, I'm a little bit far down. There we go. Okay. So what did I do here? And how does this help me? So, first of all, if I am in the case, so as I said, my hope is to address this possibility that no such interval where this is true exists. So note that if this is true, then what I get here is actually the same as what I got before. Okay. But if this is, say, not true, so if f of x is equal to f of x naught, then what do I get here? So if f of x is equal to f of x naught, then it turns out that both sides of this is equal to 0. Okay, so let's just see why this is. So if f of x is equal to f of x naught, it's clear why the right-hand side is equal to 0. So then why is this side equal to 0? Well, if f of x and f of x naught are the same, then this is g composed with f of x naught minus g composed with f of x naught, so this is also 0. So this expression also holds even when this isn't true. Okay, and so that's why. So now we have an expression that holds in any case. So take limits. All right, so if you take the limit of both sides as x goes to x naught, now going back, let me pull this back here. So if I take the limit as x approaches x naught of both sides, what I get on the left is the derivative of g composed with f at x naught, and what I get on the right is the derivative of g at y naught, but y naught is f of x naught. So this is the derivative of g at f of x naught times the derivative of f at x naught, which is exactly the statement of the chain rule. Okay. So when you're reading through this in the textbook, it's easy to get kind of bogged down in the details and the bookkeeping. But basically, the second you write that long expression that we started with, you're done almost, because that almost gets you there. There's just a little bit of stuff that needs to be nailed down after that. Okay, so I'm going to do one more application of this, which is, as I mentioned earlier, it's the example of x to a rational power, and then that will be that. So What I may do, since we missed Tuesday's lectures, I may record a lecture over the weekend and post it, and I would, in that case, of course, I would let you all know. So in general, pay attention to the Elms announcements and pay attention to the syllabus page. Um, I'm going to start listing these things, and also now that you've seen the YouTube channel, you can have a look at it. I'm going to make public some of these things after they're recorded and uploaded to the account. I'll make them public so you can actually use this account. Kind of is like this is where I'm going to post everything. This is where everything is going to be posted. Okay, so like I said, one more application, or one application of this rather, of the chain rule, together with the stuff we did earlier. So for a rational number r, define h of x to be x to the r for a positive x. We don't want to get into any issues here. So then h is differentiable. And h prime of x is r times x to the r minus 1. So you get the thing that is analogous to the power rule for both, or for generic rational powers, I should say. Right. In fact, you know that you even get it for irrational powers, but we'll see that later. So anyway, how does this work? What's the idea here? It just came right after the chain rule. How am I going to do this? My idea is power rule plus proposition for x to the 1 over n plus chain rule. Okay, that's my proof. Why does that work? So let's remember here. We know what the power rule is. I don't have to go over that. This proposition for x to the 1 over n, what did that tell you? That told you that if you had a function, we'll say g of x, which is x to the 1 over n, what was g prime of x? And g prime of x is 1 over n, x to the 1 over n minus 1. Okay, so we showed that using our theorem for computing derivatives of inverses. Okay, so then what does that have to do with chain rule? So then if f of x is, say, x to the m, how are these things related? Well, for a rational number r, we know that r is m over n for some integers m and n. Okay. All right, so then what's the idea here? The idea is, note that h of x, which is x to the r, that's x to the m over n. I can write that as x to the m to the 1 over n, which means I can write it as g composed with f of x. Right. Now I use the chain rule. Okay, so using chain rule, what do I do here? So by the chain rule, h prime of x is the same thing as g composed with f prime of x. But by the chain rule, this is g prime of f of x times f prime of x. Okay, so g prime is 1 over n times x to the 1 over n minus 1. But that's g prime of f of x. So this is 1 over n times x to the m raised to the 1 over n minus 1. okay, times f prime of x. F prime of x is m times x to the m minus 1. Moving over here. This is m over n times x to the m times 1 over n minus 1 times x to the m minus 1. So then these things, how does this work? This is, so now we're remembering our exponent rules here. So this is x to the mn minus m plus x to the m minus 1. So what does this become? This becomes m over n times x to the m over n minus 1. But, oh, that's r x to the r minus 1. And that's it. Okay. All right. So that's all of 4.2. I believe by the end of next week we should have entirely finished chapter 4. Is that hoping for a little bit too much? Like I said, I'm going to post a lecture over the weekend. Yeah, we'll definitely have finished chapter 4 by the end of next week. So I'll start on chapter 6 after that. So we'll go directly to from chapter 4 to chapter 6. So anyway, I'll hang out for like another 5 minutes in case anyone has any questions. But that's pretty much all I wanted to say. So like I said, I'll be continuously updating the ELMS page and the syllabus and all of that to make sure you guys are kept up to date, basically with everything that's going on. But yeah, this is more or less how things are going to proceed for the foreseeable future. If I come up with something that I think would work out better, would be either more convenient or would just be a better way of doing things, that I may switch some things around. So not everything is set in stone or anything, but this is kind of the general idea. So yeah, so that's it. So I will see you all. Like I said, the plan is Tuesday at 12:30, but I'll post some stuff over the weekend. So anyway, so yeah, like I said, I'll be around for a couple more minutes and then I'll end the stream.